So there's going to be mistakes made. You may throw out some variables based on statistical differences that may not be really profound. But by and large, the vast number of the decisions that are going to be made are going to be the correct ones. And this is also easy to, with the right methods, easy to correct for. And in lots of situations, and remember the situation we're looking at, 228 variables, there's lots of situations that people deal with a lot fewer variables where backward selection may be much better suited. The point we picked is actually kind of a special point. It's this green line right here. In normal circumstances, that looks like an outlier. We would dig into it a little bit more and figure out why that point is happening. Maybe a very low number of trees were built for some reason, and we'd want to understand exactly why that peak is happening. But it does occur, in the general peak also. But again, versus a true out-of-sample data set, you might not quite see that level of performance. That might just be some statistical variation. Are there any questions or? Mm-hmm. Yep. Most definitely. Most definitely. Most definitely. And I concentrate on to mitigate some of the overtraining, just resampling, which does a great job. You can also, a really good tact is, and it's a little bit harder to implement, is having a validation data set that you basically select randomly from. And that's actually a much better test. And also, if you're able to do more than one test, in different validation data sets, that's great also. It just takes more time. Any other questions? Or?
You said, though, that you were doing that along the way. The subsample.
Yes.
Is the subsample
Yes. And I'll tell you right now, it does in this situation, does a perfect job. It does enough for mitigating. We have a very large out-of-sample data set here that we're able to score and confirm that the line looks similar to this. Obviously, I didn't want to score 228 models, but it really does enough. And I do realize there's probably better schemas for that also. And what this resampling does, though, it's adding this type of noise to it. And if you don't resample, the test curve is going to be much flatter, and you're going to see what appear to be much better trends, but they're not going to be, you're going to be overtraining, though. But on the same sample, this is going to be very, very much more monotonic and very, a lot smoother. Okay, so a comparison between the three methods. This is just the test ROC. Again, it's a centralized moving average on all three of these types of selection. And as a centralized moving average, they should converge at the same point, but since it's a moving average, there's some delta. So what you can really see here is, the differences specifically between backward and forward selection. You can really see that in this type of a problem, forward selection does a great job. Now, I guarantee that this 25 variable model could be improved upon. Forward selection, one of the big pitfalls that I'll go over here is that it doesn't see highly interactive variables. So in cases, when you're doing your test, you're only seeing how the variable being tested interacts with the set of variables that have already been selected. You're not seeing how the variable being tested may interact with a set of variables that aren't in the model. This can be definitely you can try testing for key interactions. You can try testing them in groups. There's a lot of different ways that you can address this weakness. Also, sensitivity to, what we're seeing here is just, pluses and minuses of each, the strengths and weaknesses of each technique. So forward and backward selection, they all do a great job in sensitive to identifying unstable but heavily utilized variables in TreeNet. This is kind of the, I want to say downfall, but this is one of the weaknesses of variable shaving. But it's a weakness that can easily be overcome by really knowing the data well. And a lot of testing also. Sensitivity to heavily interactive variables. Backward selection does a very good job at this because, again, if there's a really important interaction, you'll, as you're removing it, you won't, if it does add significant performance, you're not going to remove it. So that's one of the key benefits of backward selection. Forward selection, like I just mentioned, doesn't really do a good job of this. Guard against composite variables. Forward selection, you have to be careful with this. For these composite variables, in this greedy fashion, can be introduced into the model fairly early on, even though in the end they're not going to add any. There's plenty of good surrogates that you could use in replace for those composite variables. Backward selection, again, isn't really, it's not much of a deal for backward selection. Processing efficiency, that's a big one. Shaving end steps, very easy. Forward selection, I'm also giving it a plus because usually you hit a stop condition fairly early on in your process. You very rarely would need to run this out to 228 variables. Backward selection, of course, since the optimal solution far closer to variable 1 than variable 228, it's going to take a long time to run in most cases. Suitability for large number of variables, this is, goes into the one above. Really, forward selection is really the winning method for a large number of variables. Okay, so devising more advanced algorithms. Obviously, there's lots of strengths and weaknesses between these different approaches. You can really solve most of them just by combining the two procedures. Like I said earlier, backward selection may make mistakes earlier on, but if there's some forward selection steps mixed in, they can correct for those mistakes that are made. So, if you throw out a variable that is ultimately important, you can go through a step of adding it back in later. This can combining the two procedures can really take many forms. You can grow out to, let's say, 30 past your peak and then do a series of backward selection steps. There's really a lot of different ways you could go here. Controlling for differences in parameters over variable space. This is a very important one. The optimal parameters at variable with 15 variables is fairly different than the optimal parameter set at 228 variables. So controlling for this is probably one of the more complex items, but it will probably add the most lift when rolling it out. Decision metric augmentation. So in these examples, I was using the ROC as applies to the test data set. You could also bring into effect some sort of a measurement of how well something generalizes. So the delta between the test, the learn and the test curves is a good metric. So you can avoid, in this instance, some of these variables that are unstable, where there's a large delta. And really, you're going to want to probably still decision largely on the test ROC, but you can bring in the delta between the test, the learn and the test by, attaching some sort of a weight to that difference and subtracting it from the test ROC. And this really leads to what you may find is if you're concentrating on more stable variables in the beginning steps, it can lead to more stable variables more stable models in later steps. And you're looking at the on the previous slides we were looking at a fairly large difference between the learn and the test. So there's a lot of room for improvement in just minimizing that. Variable sampling, this is really concentrates on efficiency. Really, what we did here was we ran over 26,000 models in each of these methods. A lot of those tests we didn't really need to do them because we tested a lot of these variables in earlier steps, and that those earlier tests are somewhat determinant of how those variables would perform in later steps. So you don't need to, at every step, necessarily test each and every variable. And in our experience, you can probably cut down the number of model tests down, 40, 50%. So very, very significant improvements. The internal resampling of learn versus test, this is just to mitigate overtraining. There's various techniques for this. And finally, ICL. This is really the biggest thing you can do is just apply these methods to picking and choosing what interactions to include in your models through the ICL language. And that's going to be a major improvement of what we're seeing here. So, in conclusion, this is a key component of TreeNet model optimization. It's not the silver bullet. It's one of many. Again, you're improving performance, interpretability of your models. Backward and forward selections, important building blocks for, these more sophisticated methods. You're going to get a lot of the performance, but you're definitely able to bring out a lot more performance with more advanced techniques.